everybody for joining us today for a live webinar in collaboration with Atlantium. My name is Elinor and I lead the brand and growth here at SeaNovation. Before we begin, a quick note on participation. You're all very welcome to introduce yourselves in the chat and share your LinkedIn profile so others can connect with you. You can also enter questions in the chat at any point during the session and we'll address them in the live Q&A at the end. So SeaNovation is the International Center for Innovation in Biotechnology and Aquaculture.
Yes.
Welcome to Eilat, Israel's southern frontier, where desert meets sea and innovation meets opportunity. Here, at the heart of the Red Sea, unique ecosystems remind us how fragile and how resilient our world can be. Protecting and sustaining them requires bold new ideas. That's why we built SeaNovation, an innovation center chosen by the Israel Innovation Authority to support startups from idea to impact. We connect entrepreneurs with mentors, grants, and real-world infrastructure to test and scale their solutions. From labs and aquaculture pools to cutting-edge marine research, SeaNovation is shaping the future of food, water, and sustainability. Jump into the deep end of innovation with us and be part of the ecosystem.
All right, so we turn real operational engineering and research challenges into pilots, solutions, and impact, all while leveraging the unique assets of the Eilat region. We are located in the southern tip of Israel, and we're supported by a strong national and regional ecosystem, the Israel Innovation Authority, the Ministries of Economy, Agriculture, and Food Security, the Ministry of the Negev and Galilee Development, and the Ministry of Regional Cooperation. We're also strengthened by our regional and professional partners, including Aquabeta Site, Ardor Management and Holdings, Ben Gurion University of the Negev, Aquaculture, the National Center for Mariculture, and the Israel Ports Company. We have ongoing support from the Eilat Municipality and the Eilat Regional Council. We support founders across 3 stages of growth. First, a pre-accelerator, where founders come in with an idea, we help them shape the product, understand their market, and set their business model foundations. The goal is for clarity and early validation. We then have the AquaBoost Accelerator. This is for teams ready to build. They develop their POC or MVP, run early pilots, and refine their model with real customer feedback. And finally, we have the Wave Up Scale Up program. This serves startups already in the market. We support their expansion, connecting them with strategic partners, investors, and new markets to help them grow sustainably. Today, we're pleased to be collaborating with Atlantium Technologies and leading industry experts, where you'll be hearing from directly in the session. At SeaNovation, our role is to bring real challenges to the table, to help our community understand what's happening in practice, and to explore solution pathways that are grounded in real-world conditions. This webinar is part of that mission, connecting research, technology, and industry experience so together we can move forward to a more resilient and secure aquaculture systems. With this said, thank you for listening to my short introduction. I would like to introduce Yifat Mazuz, the SeaNovation CTO, presenting the introduction to the webinar session and moderating the rest of the webinar. The table is yours, Yifat.
Thank you, Elinor. Thank you for the introduction. I'm very pleased to be being here in the webinar, to participate in the webinar, and to be the newest team member in SeaNovation. It's good to be back home in Israel and joining this group of people, this talented group of people. For everyone, good morning, afternoon, and good evening for everyone, and welcome to today's webinar. Today today's session will be focused on off flavor in aquaculture and specifically in RAS system. The topic of off flavor in aquaculture often discussed quietly and on the side of operation and farm to farm basis, but very rarely we address the topic as a system and a scientific on a system and scientific level, and almost never from a global perspective to these challenges that I think the majority of the people joining us today have some contribute to this topic. My role today is also to frame the topic. I will do it in a short presentation from my side, and then I will lead the way for the professional expert that we have today to elaborate and go deep into the application and the technical and scientific solution for this topic. I'm going to share my screen now with the presentation. Give me 1 second, please. Second. Okay. Okay. So the first slide that I want to talk, like I said, it's a framework, so I'm not going to elaborate into the science too much. I'm just going to give the highlights of this topic. So when we are talking about off flavor, we are talking about components, chemical components that we have from a secondary metabolism from biofilm and bacteria in our system in the water. It's not only related to aquaculture, it's also related to wastewater and drinking water. So it's a mutual problem, but we will focus on the aquaculture aspect. The main things when we are talking about off flavor, we all need to remember that is a risk for the aquaculture, but not a restriction, because it's not a toxic component. It's not under food regulation and restriction, but it is a problem when we commercialize our product, fish, shrimps, or crustacean, whatever we are in the main protein that we are cultivating, growing, and then at the end of the day want to sell. So, like I said, it's a secondary metabolism component that coming from bacteria. We have two main family characters that influence the off flavor. One of them is the actinomycetes, and the other is cyanobacteria. There are more bacteria today that is revealed to relate for the off flavor, but this is the most common and big group. The bacteria, the secondary components from the bacteria, it's chemical components, what we are calling Geosmin, and the 2-MIB. This is the main components that give this off flavor that we related in aquaculture, the muddy, earthy, sometimes metal flavor, and also smell that comes from these chemical components. When we are talking about biofilm that capture the bacteria that causes the off flavor, we are more related it to recirculated system and closed system because of the nature of the system and recirculated water that makes the flavor and the off flavor staying in the system from batch to batch, from cultivation cycle to cultivation cycle, and it could go along with the system. So if I need to frame it, it's a problem that is we related it to water quality because of the presence of the bacteria, but mostly I would say it's a problem that comes from a figuration and engineering of the system that working together with the existing of the biofilm in the system. There is there is a threshold of the smell, but there is, like I said, there is no regulation threshold. So from the minimal limitation, the product could be restricted. From that point, I will, like I said, it's a frame, so I will just do an overview of the problem. So when we have the problem, we also have the economic effect of the problem in the aquaculture. So the aquaculture market for today, if we close in 2025, we're talking about probably around $300 billion market value, and we are growing more than 100 million tons of protein. It's including fish, shrimps, crustacean, and the small protein that is combined with the big one. From that aspect, we have uh, um, billions of dollars lost annually from the off flavor. We are not categorize it by specific topic because it influences the majority of the aquaculture RAS system, and it influences in major aspect of the operation from the cultivation side, labor, production, timing that we put in offline, biomass that we are not selling, so off the shelf biomass that is not selling. So the total of all of these aspects give us billions of dollars of annual loss. At the end of the day, if the product is downgraded, the customer is not buying it, and all the value change is drifting into loss. There is a case study that I think the majority of us from the industry knows about it and heard about it. The Nordic Aqua Partners in 24 million of dollar lost from operation to shut down until re-establish the operation after really infected system with biofilm that influence the biomass. And from the economical aspect, I will go and just do a quick innovation. So today we have the conventional treatment that is going from a water quality treatment before even seeing the problem in the system, maintaining good quality treatment and operation, and also using UV, ozone, all this equipment that can eliminate the bacteria from the system, but also we needed to take into account that we have a sensitive and delicate balance between what we call a good biofilm or a bad. I don't want to use the word good and bad, but we do identify the biofilm as part of the system, something that is value if we're talking about from the aspect of nitrification and denitrification, but also when we look on the aspect of existing cyanobacteria and other bacteria that could lead to the chemical components of flavor. So we have the equipment that can treat this bacteria. We have a few pilots around the world that try to treat the the off flavor from different aspects: oxidation pilot, electricity pilot. We have a lot of ongoing pilot from 25 that just started in the microbiome aspect to combine specific formula of bacteria into the system pre-cultivation and in during the cultivation. But this is where we stand in the innovation world of flavor. So this is just a brief understanding what we are dealing until today, until the beginning of 26 in the off flavor aspect in the RAS system. From just sorry. So from this aspect, I will continue and join in our speakers to take it into a deep overview of the problem and the specific RAS system and of flavor. Our first speaker would be Micha Eschar, is a water engineer, has an extensive hands-on experience in recirculated aquaculture system and abundant and advanced experience in oxidation process. He will take it with his presentation, the technical perspective on Geosmin and off flavor in RAS system. Micha, please go ahead.
Thank you. Thank you. Wait, sorry. Great. Thank you. Thank you, Yifat. Thank you, SeaNovation and Atlantium, for this collaboration and for putting up this webinar. And it's not too late also to encourage you to participate if you can in next week, See the Future 2026 in Eilat. Who am I? This is a picture of me, maybe taken last week or maybe the other year or 25 or 30 years ago. I'm an agricultural engineer. I specialize in water treatment, and I also was a fish, was a fish farmer, both edible and aquarium fish, ornamental. I'm thankful to do things that are interesting for me. And these are some of the topics I've dealt with. Now, we're talking micropollutants. This needs to be put into perspective. What does it mean, micropollutants? It impairs, it damages water quality in very low concentrations. How low? How small? In RAS, mostly we use the units of milligram per liter or ppm, parts per million. Whereas Geosmin and other off flavors, we're talking nanogram per liter, which means 6 orders of magnitude smaller. Where ppm is parts per million, we're talking a millionth of a millionth. So we can understand immediately that this needs some sophisticated equipment to analyze that typically is not available on site. And we also can understand that it's easy to forget about it. The Monod equation that we see here is meant to illustrate that conventionally, for a process, at best case, it is proportional. The rate of the process is proportional to the concentration of the substrate at best. If the concentration of the substrate, the thing that we need to treat or remove, is very small, then the conventional processes, they have a problem, and they would either be too slow or be prohibitively expensive. Where does it come from? I'm not going to give a lot about it. Yifat covered that. It's natural. One more thing to bear in mind, both Geosmin and MIB are two substances that we have standard lab procedures, protocols for them. When we go to a lab and we ask for something to be analyzed, then they need something, they need some protocol according which to work. There's dozens of off-label compounds, OFCs, and we don't have. We can test them in a university, but it's not standard procedure. So we relate to both Geosmin and MIB as tracers, as something that detects. Is detectable. So it comes from either surface water or biofilms or other sources. And also, as Yifat mentioned, and I'm sure Egal will relate to it later, biofilms are essential. One more thing is that it can be also biological filters. Biofilters can also be suspended. This also Egal can relate to, but it doesn't prevent off flavors if it hasn't got, if it is suspended rather than attached to some artificial surface. The microbial colonies attached to the surface produce protective matrix, primarily made out of extracellular polysaccharide, EPS. I can talk a whole day about that. That is sheltering the microorganisms from changing water conditions. In many cases, it can protect them also from ozone or other chemicals we might use in RAS systems or generally in aquaculture system. To the point that biofilm may release off-label compounds. In the context of Geosmin and other OFCs, the equilibrium between Geosmin in the water and Geosmin in the sea, Geosmin in the fish relates to fugacity. Fugacity is a concept from physical chemistry that is about the tendency of a substance to escape from one control volume to the other controlled volume. So in our case, it's a correction for non-ideal behavior. In our context of off-flavor, it illustrates the tendency of Geosmin to either move from the fish body, from the biomass, to the water, or the other way around. By the time the farmer sees the damage, it's too late, and there's loss of. It's not so much loss of biomass as loss of reputation. The wholesaler comes and says, "Listen, I cannot sell your fish," and this is a bummer. One more thing to bear in mind that is due to this fugacity thing. In the water, the concentration could be 1 to 10 nanogram per liter. The limit of detection in the water is not much below 1, maybe 0.5, maybe 0.4. But when in the water it is 1 to 10 nanogram per liter, in the fish it could be 500 to 1,000 nanogram per kilogram, which is already prohibitive. So, existing solutions. We just mostly, in many cases, they just move the fish from, the system water that contains Geosmin to separate tanks where you have clean, so to speak, water, such that the thing will leach from the fish body, from the biomass to the water. We have to bear in mind, though, that at a concentration of 1 to 10, like a concentration that is very low, then the fish is already tainted. This is some serious consequences. In these, how do we clean these tanks, the water in the tanks? So once the fish are in such a clean water tank, they start leaching the substance to the water. The concentration of Geosmin in the water rises, and consequently, the rate of diffusion, the rate of purging, reduces to zero very quickly, by the way. So the problem is that you have to clean that water either by applying more makeup water or by treating the water at a sufficient rate. And I will relate to it in my last slide. What do I mean by sufficient rate? Makeup water mostly has a temperature that is different from the system's required temperature. This necessitates either heating or cooling of the water, which means energy consumption. In those depuration purging tanks, you cannot feed the fish because when you feed them, feed creates metabolites. Fish excrete it to the water. You need to filtrate it somehow. So if you cannot feed the fish, you lose biomass. The fish first thing they lose is fatty tissues, which is more sought after by the market. The fatty tissues give the fish the taste. The market prefers fish that are not too lean. So this is another damage. Environmental regulations, they require maintaining water quality parameters in the discharge. This costs money, so you cannot use too much makeup water. So fish tanks dedicated for depuration, they occupy operational volume that could otherwise cater for more production. So we understand that depuration should be as short as possible to minimize losses. One more thing, a common solution is to put, a granular activated carbon. And it's true that granular GAC can remove geosmin, but then if you leave it for too long, then here's the problem. The water contains nutrients because the fish keep excreting ammonia and phosphate. And this is very good for microbial population to use this media, this GAC, as a biofilter. And as a biofilter, it creates geosmin. So there's a limit to that also. Advanced oxidation processes, this is not an emerging technology already. It is around for some 25, Atlantium can elaborate more than 25 years, more than 30 years, I think. Remember that we're talking very small concentrations. Now, the thing is, what does it do? We excite a radical source. Here I gave the example of peroxide to generate unionized hydroxyl, not ions, hydroxyl radicals. Radicals are very reactive. They're very short-lived. We talk picoseconds to nanoseconds, maybe microseconds, but not more than that for sure. And they're not selective, which means that if we have a little bit of BOD, COD, TOC, you name it, in the water, remember that when we talk COD, we talk 6 orders of magnitude higher. So if we have something that can be a radical scavenger, then the radicals would go for that first and not for the thing that we need to remove. So we need to pre-treat the water to have it clean. The advantage with radicals is that it can attack, it can mineralize even, denaturate or even mineralize recalcitrant, difficult to break substances. This is the one before the last. One crucial consideration about the sizing, the correct sizing of things. Traditionally, when you come to a process engineer and you tell them, okay, I need to do this and that, I need to keep the level at so-and-so, and the system needs to remove so-and-so amount per time. So they do a calculation that answers maybe, you know what, in a system that answers 99.9% of the events is considered expensive in process engineering. In agricultural systems, mostly you use 90 to 95% at best. Now, here's the point. So traditionally, they would say, okay, I can compromise at about 5% of the incidents. So 5% of the time, I can be off-spec. Now, what happens in the depuration tank is that when they did the dynamics, the researches and the articles and the literature we have for the rate of depuration of fish, the leaching of the substance from the fish to the water, they did it in under controlled environment. So they have limited amount of biomass with big tanks, so it is less, the population density is not so challenging. And because they want to have, they want to do a calculation, they want to publish the article. But here we talk reality, and in reality, you have much higher load, much higher biomass per tank. So the moment you put the fish inside these tanks, it affects not only the concentration of the geosmin in the water, but eventually it affects the rate of depuration, the rate of removing the geosmin from the fish to the water. So we have to bear in mind that the highest removal rate in this graph is at the beginning. And if you size the system according to the average removal rate, then the depuration will last a lot longer, because you have to size the system for the highest rate, for the 100%, for the most extreme case of removal, which happens right at the beginning. If you don't do that, then instead of maybe 4 days or 7 days or 10 days of depuration, you might end up with a depuration period of 14 days, in addition to having maybe 20% of your fish not meeting the requirements of the market, which is a huge damage to reputation. Thank you. Do you want to take the lead from here?
Thank you, Micha. We will go over to our next speaker. Our next speaker is Yigal Magen. Yigal is an independent expert in recirculated aquaculture system and waste treatment. He has more than 20 years of experience in RAS design, optimization, and troubleshooting with hands-on work across freshwater and marine system. He led pilot facility and commercial farm worldwide, so I think he's coming with the right experience. Yigal presentation will be off-flavor in RAS, constraint, effect, and particle management. Yigal, please, over to you.
All right. Hi, everybody. Let me share the screen. Second. So, good morning, everybody. First of all, thank you for everyone that joining this webinar. My name is Yigal Magen. I've been working in the aquaculture industry for actually more than 25 years, both from the technology side and from fish farm operation. Today, I want to speak about off-flavor in RAS, not as a marginal quality issue, but as a structural operation and economical challenge that affect almost every system in RAS that we have. But before diving into the off-flavor, it is important to understand the context. RAS is one of the fastest growing segment in the aquaculture, with a growth of about 15% per year. This growth is driven by water scarcity, land limitation, environmental regulation, and you can see the worldwide project planned around the world. The RAS actually is ensuring growing fish close to the market and avoiding this crazy transportation that you can see here of fresh fish worldwide. One of the most frustrating realities in RAS is that you can produce biologically perfect fish, good growth rate, good survival, even good welfare, but still fail commercially. This reason is not disease or food safety, and you can see the fraction of the publication that you can see worldwide regarding this off-flavor issue. RAS is especially vulnerable because of its three main factors: very low water exchange, high biofilm surface area. Micha and Yifat already talked about it. And actually, these conditions support the microorganisms that can produce off-flavor. even a concentration of nanogram per kilogram can be enough for human to trace it. And this is a core trade-off of RAS. The more efficient the closed system becomes, the harder it is to remove the compounds that are significantly targeted by the treatment system. Because in closed system, what TAN and CO2 and all the other is actually engineered to remove, but the secondary microbiology is not. So this is actually accumulating in the system. Off flavor is entirely let's say it's the earthy or musty taste that makes otherwise healthy fish unacceptable basically. And actually, as we talked about, it's mainly caused by geosmin and MIVs. Those compounds are particularly problematic because they are hydrophilic, chemically stable, and resistant to biological degradation. They do not volatilize easily and rapidly, and they are absorbed in the fish tissues, especially in the lipid-rich tissues. If you take the salmon, for example, this is why once it's entered the fish, they are difficult to remove. As mentioned before, it's geosmin and MIB are natural microbial and metabolites that are produced by bacteria, especially actinomycete or cyanobacteria, and even some protozoans. And as Yifat said, there are many versions or many other compounds for off flavor, and we basically measure it for MIB and geosmin because this is the GCMS project that we have. But I guess there are some that are there, but we don't know exactly what they're doing. But in Earth, those organisms are thrive in the biofilter, in the biofilm, and always there is an organic rich zones, and making the off flavor a structural risk and not an occasional contamination. The standard mitigation is purging, or also called depuration, meaning the fish are transferred from the grow-out RAS to dedicated purging tanks before the harvest. These units operate with a very high water exchange, off flavor or even flow through condition, and the goal is to keep the off flavor concentration in the water close to zero. Those off flavor compounds enter the fish mainly through the gills and accumulate in the lipid rich tissues, and the operation relies entirely on diffusion, as Micha said. Compounds move from the fish tissues back into the water only if the water concentration stays very low for a long period of time. This is why the purging takes days or weeks and not hours. But then actually this comes with a cost. When you go into CapEx, purging requires dedicated infrastructures, tanks, piping, oxygenation, degassing, and also sometimes water treatment. And this is actually an additional CapEx that have to be on top of the grow-out system and not instead of, meaning that basically when you're going into a RAS design, again, rule of thumb, about 15% of the surface of the farm is dedicated to RAS. And actually in this, you're consuming between 500 to 1,000 liter of water per kilogram of fish. This is a huge amount if you compare it to what RAS is designed to do. So you're saving water through the grow-out period, and then you're spending all of it in the purging section. Now, if you go to the operating expenses, then it's first purging uses about, as I said before, 5 to 1,200 liter per kilogram of fish. It's about 3 to 10 times more than the RAS itself. You're investing in energy for the pumping, for recycling, and labor. Then there is also the biomass loss. During this purging, fish are usually starved and lose everything between 5 to 10% of the body weight. There are some new procedures when you're feeding 0.5% just to maintain, but still those fish are losing their weight. And not only losing their weight, but this period of 10 days, they're actually not gaining weight. So the loss is even higher. So this is an immediate revenue loss, in addition to harvest delayed, grow-out cycle are extended, and tank turnover is basically blocked. So when we combine all of those biomass losses and the extra grow-out time and the time spent in purging, off-flavor mitigation typically accounts for about 5 to 12% of the production cost. I know Yifat talked about it, but this makes the purging structural, economical, and penalty in RAS. So this is why it's very important. So when you combine the biomass loss and the time spent, so you can see that you have to do the day-to-day off-flavor management and in the commercial RAS, meaning doing the routine sensory and checks by trained staff, monitoring the core water quality parameters, mainly the TSS and the ammonia, maintaining the biofilter stability and avoiding any operational shocks. Event-based testing, meaning every once in a while do the Geosmin and MIB test for before harvest, and regular removal of solid that actually can be the basis of the accumulation. These actions can reduce the risk and allow early detection, but they do not remove the off flavor once it is in the fish. So the key operational principle is to act early rather than react at harvest. Prevention and early detection are far cheaper than extending purging. Once the off flavor is present in the fish tissue, operational options becomes very limited. So this is why you need to actually extend all the parameters. So I wanted to take you for another option that, as discussed before, purging is let's say the most commercial being used as today, but there is another option. This is an electrochemical process, mainly designed to actually treat ammonia. But as a byproduct, we saw that actually it also can remove Geosmin and MIB. And this is an alternative approach. It belongs to the family of advanced oxidation process that Micha described. Instead of relying on dilution and starvation, this approach actually destroys the off-flavor compound in the water. We did several trials in the company by Fission when I used to work there. And first, basically, the water goes through an electrical chemical chamber that actually generates those radicals. And as you can see from the graph, this is actually a lab result. When you can see the blue one is the ammonia removal, and the orange is the MIB, and the gray is Geosmin removal. And see that when you're removing the ammonia, we're basically removing about 80% of the MIB and Geosmin in one pass through the electrolyzer. And this was a lab result that we did. And then we push it further because the idea is try to do the purging while feeding. So there was an experiment that we did to demonstrate the purging while feeding. We used the trout because we don't have salmons in Israel. Stocked about almost 100 kilo per cubic meter, and did the feeding regularly. And basically, we did a spiking, meaning we spiked the water with MIB and Geosmin at the ratio of 800 nanogram per liter for 8 hours. And after that, we start running the system. And here you can see the results. This is the MIB and Geosmin from the water. And as you can see, in day zero, at time zero, you can see that we managed to spike the Geosmin and MIB in the water. And in a period of 6, we removed the MIB, and in 8 days, we completely removed the Geosmin when the detection limit is 5 nanogram per liter. And this is in the water. And when we did it tested in the muscle and in the skin, so you can see this is the MIB and this is the Geosmin. You can see that the MIB was removed from the muscle in 3 days, and in the skin in about 5 days. And the red line is actually when there was 0 nanogram per liter in the water. And if you go to Geosmin, it's a bit more stubborn, and you can see again after 11 days it was below the 5 nanogram per liter. So basically, what the system does is actually remove or replacing the water replacement by actually oxidizing those MIB and Geosmin, and brings it to 0 concentration in the water, and there's the ability to the fish to depurate those back into the water. And this has been done while feeding, meaning that you can actually not only do the purging with saving huge amount of water, actually continue feeding them and not only lose, but actually continue gain weight. We did this project also in other places in the world, in Sweden, and it was very similar results. So the purging is still the only fully proven commercial method for removing off flavor. But among water treatment, AOPs are the one that actually have the most way to work with it and to gain this way of removing the off flavor. And AOPs are considered ozonation-based, UV combined with peroxide water, electrochemical oxidation, and other like fentanyl and plasma that are very in early stages of research. So when you summarize it, if you're going, what is the standard widely used? So the technology is purging, sensory monitoring, harvest daily, and purge decision. All these procedures are being commercially. Um, there is some companies that using activated carbon and even ozone as a side stream to reduce it. Some actually having ozone is UV, and I guess that Atlantium would describe in more in detail. And there are several pilots that have been done with electrochemical oxidation, and the other research, ultrasound and feed additive and so on. So basically, this is summary of what can be done. If you have any question or take it from here.
Thank you, Igal. We're gonna, if there is a question to Igor or specific question on his presentation, we will do it at the end of the session. We will go over now to our next speaker. It's speakers, both will be joining together. Final speaker will be Isaac Rosenberg, the CTO of Atlantium Technologies, and Amichai Felder, Vice President of the Innovation of Atlantium. Isaac led multidisciplinary R&D teams developing UV-based water treatment technology. His sector is municipal, industrial and marine application. Amichai is as an expert in water treatment process and thermodynamic leading Atlantium application team. Their presentation will focus on Atlantium solution pathway and technology approach when we're talking about off flavor in RAS. Guys, the floor is yours.
Thank you. Let me first try to change my screen. A second. Okay. Now you can see it in a full presentation, I assume. Okay,
No,
so
Yitzhak, you didn't share the correct screen. We see you. You need to select the screen that
a
you are
second.
presenting from.
So, Ami said it's now okay, is it? Okay.
Yeah,
Okay,
it's
so
okay.
okay, thank you. So we are already being introduced. First, let me introduce Atlantium. We are a UV-based company introducing our technology under the name HOD UV to different industries. The aquaculture is one of our main market area. As you can see, for more than 20 years, we have a vast experience in providing our solution for the aquaculture. So we have more than 1,000 installations globally. Regarding what we are doing, so in the aquaculture, so besides providing to the common applications like RAS for mitigating the pathogen and other microorganisms, preventing biofouling, preventing other issues with the fish, we also engage in research programs, international, and some research that we are doing by ourselves in order to further explore what the technology can do. or what it cannot do. And so this is how we are promoting our solution. Regarding some of our customers, global customers, so you can see some of the logos of them. So we are proud to be part of the big players in the aquaculture industry. For example, one of the territories is Norway. So as you can see, our installations there, a different application, including intake water, RAS, and so on. And this is an example of Canada. So you can see our installations over there. So from this point, I'm giving the spot to Ami to talk about some results that we have in the area of the off-flavor. Ami, please.
Thank you. Just make a mark that you see the full presentation. Okay. Hi, thanks, Itzik. Okay. So just I want to summarize. I hope I will manage the time constraints. I want to summarize some of the things that were said earlier here. So first of all, Geosmin is hydrophobic. That means it's accumulating in the fish lipid tissue rather than remaining in the water phase. Second, we assume that Geosmin can be removed can be removed from the water by using AOP UV, as Micha said. Third, and this is the critical here for the puration phase, Geosmin is not permanently trapped in the fish, as was shown by Eagle. It diffuses from the fish tissue back into the water. Now I know that it's via the skin. And it happens when the surrounding water Geosmin concentration is kept low. So putting these few assumptions together leads us to our working hypothesis. If we recirculate water through an intensive Geosmin removal stage, we can then maintain a strong concentration gradient between the fish and the water, and that should lead us that should result in a faster and better depuration phase. So the concept is recirculating the purging tank, where water is being continuously treated by UV. By this, we drive the diffusion out of the fish without stressing the fish, of course, and allows the purging phase to be treated as a controlled process step rather than just waiting a period of time with uncertain outcomes. So implementing this technology, it raises a few, okay, it's shown, okay. It raises a few, several practical questions. I will show, I'm showing some of them. I will not give answers, just the questions. But first, how do we size a multi-stage process? And I think Micha presented a slide about it. So as I said, the Geosmin diffuses from the fish to the water and being destroyed by the UV. So should we size according to the maximum initial concentration, or maybe look at it as like a total dry weight of Geosmin per volume to be treated at a certain time, and by this deduce the kilowatt of the UV. So these are two, it's a typical two approaches of sizing such a process with a closed loop and the UV. Second, fish welfare, of course, this is not non-negotiable. Of course, any oxidant exposure must be fully contained within the treatment loop, with zero or close to zero residual entering the tank. Third, we must consider the scavenging agents, especially here nitrate and organic matter. So these two can compete both for the hydroxyl radicals and also for the light itself. And lastly, and it relates to the previous one, I want to give you an example here. This is also a typical key design choice for us as a medium pressure UV provider. So now you can see, wait, I'll show the marker. Is it shown? No, not yet. Okay, so this is the typical emission spectrum of medium pressure UV. Okay, so in black, this is the emission spectrum of the medium pressure UV. In blue, you see ozone absorption spectrum, and in red, you see the hydrogen peroxide absorption spectrum. So which one should we use? I mean, the hydrogen peroxide is easier to handle. It's safer to use. It reacts nicely with the UV, but as you can see, the absorption peak is in the low 200 nanometers, which is also, by chance, the nitrate absorption peak. And so in purging water, we can find nitrate. It can possess some efficiency issue. Ozone is stronger oxidant, especially if you consider that the absorption peak is at the 250 nanometer, which is not or less influenced by the nitrate. Okay, so as I said, this is a typical trade-off between handling issues or safety to efficiency of the process. And in the pilot that we did here in Atlantium, we used the hydrogen peroxide. Okay, so Atlantium conducted a fish-free pilot study where we spiked Geosmin in the ranges of few dozens of ppt, nanograms per liter, in the water. This allowed us to isolate the chemistry without the biology effects. And the water media was such that we received from one of our clients as a preliminary phase to a full-scale or larger installation. And it represents a typical purging water chemistry. So the pilot was composed from 2 tanks. Wait. Okay, so we have 2 tanks, a pump, flow meter, and a UV, 1 kilowatt UV. And the purpose here, we wanted to test the influence of UV transmittance, TOC and nitrate concentration on the Geosmin removal efficiency. But not only, the goal was not just to show the removal of Geosmin, because we know that Geosmin can be removed from the water using AOP UV. We wanted to understand the process sensitivity and scalability here. So this is why we use 2 tanks in order to understand the per pass removal. Okay, and some of the results. So I'll just touch, first of all, at high UVT, Geosmin is predicted to be treated very nicely from 30 to 50 nanograms per liter to below 10 nanograms per liter in one pass, not in recirculation, in one pass. It allowed us to understand the mechanism here. Even in this held true even in the presence of nitrate, which was lower in efficiency, but still we got in one pass between 20 to 6 ppt. And later on, we reached in both cases to below 1 nanogram per liter in the water, which is very good for the diffusion phase. This is as far as the results. And the next stage, to install a 30 kilowatt unit for treating fish purging tank. It will happen in Asia in a few weeks or so. And the goal, of course, is to shorten the depuration time. So it would be very interesting. Stay tuned for it. Okay, I think I managed the time.
Thank you both. Okay, so we are finished with the speakers session, and I want to thank all the speakers for the knowledge and the explanation. We will move on to the questions session. I know that if someone has a question, they could add it to the chat. I'm just gonna go over it now. And also, if there is a specific question to specific speaker, we're just gonna connect between the question and the speaker. Let me just go over to the chat. Just okay. I see there is one question here. Mariana asking, does electrochemical oxidation works in water with low salinity? She mentioned 3 and below 3 ppt. I think if it's Micha can answer it, or
Yes, with pleasure. There's one one that I can think of is that electrochlorination is a little bit more difficult to control at low salinities, but other than that, advanced oxidation doesn't have a problem. To the contrary, advanced oxidation might have less radical scavengers in less saline water. The most important factor in advanced oxidation processes is to pre-treat the water for dissolved organic matter and, of course, particulate. I hope this answers.
Let me add,
Yes, of course.
electrochemical process usually needs the chlorine in the water in order to generate those. We did some work, and actually we work with up to 5 ppts. It's possible. It means you need to generate a special coating on the plate of the electrolyzer. The lower salinity is, the less efficient the electrooxidation in electrical consumption is, but it can work, but with low productivity. So we worked many years with 10 ppts. We did some work with 5. Again, it depends on the coating of the electrooxidation chamber.
One more thing,
Thank you.
there's adsorption media that also engages direct current on the surface of the adsorption media. There's a product offered by a British manufacturer. If anyone's interested, I have no interest in that, but I don't remember now. They also can do that in pretty modest salinity also.
Thank you both, Igal and Micha, for the answer. There is one other question. How much depuration time can you save with ozone and UV? I think Michai or Isaac.
I can answer. The short answer is that we're aiming for 50%. So cut in half. If between 7 to 10 days, we're aiming for 3 to 5 days.
Okay, I think for now we don't have any more specific question. If anyone in the audience have a question they want to pop up now, individually can join with a question. If not, Elinor, I think I will pass it to you to close this session.
Wow, thank you very much to all of our speakers, Micha Eschar, Igal Magen, Amichai, and Yitzhak from Atlantium. This was a real opportunity for us at SeaNovation to collaborate on this webinar and explore this topic further. We are always looking for new ideas and solutions, and we are building an ecosystem to help promote solutions in aquaculture and now in off flavor as well. So I will be emailing you all with presentations of today's session together with a recording once it has been lightly edited. And you are always welcome to reach out to me or anyone at SeaNovation with any questions that you may have or any collaboration opportunities. We are always here to connect. Thank you again for everybody. Over 93 people had joined us today from across the globe, and it was a very inspiring session. So I thank you all for coming and being part of this community in aquaculture.